Okay, hello. It's a pleasure to be here again. Unfortunately, it's me again. So I've been here last time, and this time Sashko hoped to be here, and he wants to tell you a little bit more about deep learning, but in a way how we can interpret it and how we can actually squeeze something out of this deep learning model that they are usually hard to interpret. So, but instead you are stuck with me, and I will tell you today a few things how we can implement reinforcement learning in TensorFlow. So, quick survey, how many of you have ever heard about reinforcement learning? Okay, not bad. Are you using it on daily basis? Are you like, you have your own favorite framework? If anyone, please raise your hand. Okay, so not that many people. Okay. So let's start. So the agenda for today, really quick introduction, then few examples, very brief introduction to reinforcement learning, and I will just transition to the core topic of today's presentation. This is TF Agents. This is a library developed at Google and open sourced by Google, which helps in rapid development and deployment of reinforcement learning algorithms. And then we'll move to two simple examples, how to use TF agents and another library developed by the OpenAI called OpenAI Gym. And last but not least, replay buffers, how they can be of help, and a quick wrap up. So, the reinforcement learning is pretty hot topic, I would say, for the past couple of years, but in AI, which is not, I think it's kind of a hot topic. But how many of you have heard about recent developments in reinforcement learning, something called an AlphaGo algorithm? Have you heard about it? Okay. For those who didn't, there is a game called Go. They say that it's much more complicated than chess, and it's really harder to master than chess. There are not that many figures like in chess, just black and white rocks that you put on the scoreboard. So, for a long time, the computers were not able to defeat the grandmasters in Go. But beginning with Google DeepMind team, they started developing algorithms. One of the first, I believe, that was able to achieve a master class in Go was actually AlphaGo. But that algorithm used a lot of human input. By that I mean that they gave it a huge database of possible movements of games that human players played in the past for it to learn and to master the game. And the next development was something that's called AlphaGo Zero. So how do you think? How many data points the AlphaGo Zero used to train itself? Because nowadays we are talking about big data, we're talking about gigabytes, petabytes, terabytes of data. How do you think? Was it like hundreds of terabytes, petabytes, something less? An idea? Yeah, yes, exactly. We'll come back to that in a moment. So this is one of the, I think, really greatest achievements for reinforcement learning in the past couple of years. Something also worth to mention, mastering Atari games. I think at least some of you didn't have a chance to play games on Atari. I did. It was really cool. And the reinforcement learning algorithms also proved themselves to be able to defeat human programmers. If you play games like StarCraft 2 or Dota, they are pretty complex games. For example, in Dota, where you have 5 versus 5 players, the reinforcement learning algorithm will have to master 5 individual characters that have to collaborate in order to achieve a victory. So this is not as easy as it sounds. It's really, really tricky. But anyway, in StarCraft 2 and Dota, computers have beaten pro gamers. Now there should be a video about AlphaGo Zero, but we have, at least I have small troubles with internet connection, so I will just skip to the wrap-up about what was on the video. You can just Google the video for yourself, or just try to Google for the Google DeepMind, and there are tons of really cool stuff for you to see on the web. So, what AlphaGo Zero accomplished? So, first of all, AlphaGo Zero defeated the previous algorithm, AlphaGo, 100-0. So the previous algorithm never won. So it outperformed it pretty nicely. Second of all, as you mentioned, AlphaGo Zero was teaching itself Go without human knowledge. So no knowledge about Go whatsoever, no knowledge about strategy whatsoever, and it learned all the things that gave it an advantage and gave it the ability to defeat human super champion in Go. And it actually achieved the world-class proficiency in Go in 3 days. So I bet none of us could do the same thing. What's more, it also required less hardware and less training, maybe not samples, but less training games than the previous algorithms. It's like nearly 5 million games versus 30 million. So this is really huge. Another example, something called AlphaStar, again developed by Google DeepMind. They used a modified version of StarCraft 2 game and basically created a pretty fancy artificial intelligence to compete with human players. On this replay, part of the replay, you can see AlphaStar playing versus a pro gamer with his nickname is Mana, and he's like a super master of something in StarCraft 2, so it's not easy to master the game. And the algorithm is not cheating. This means that it doesn't have any advantage like a normal AI in StarCraft has, like it knows where all the opponent's units are, what they are doing, and also computer gathers minerals even twice faster than a human being. In this case, AlphaStar just watches the game as a human being would. He has no information about his opponent. Well, actually, it sees his opponent's units and movements as a human would do. And to add one more thing to that, the guys from Google DeepMind also introduced a latency, because the computers can actually take an action immediately after seeing something. So it would be a bit unfair for the human being to compete with that, with zero latency. So in this case, I think it was like 400 milliseconds. So the computer could possibly react faster and gain even more, I would say, beat even better players than Mana. And here you can see we have a neural network that is trying to predict the outcome of this competition. It's trying, it of course tells what units should be trained, how many of them should there be an expansion or whatever, and in real time you can also observe the predicted probability of winning of this algorithm. So this is pretty cool. And as you can see on this chart, it took 14 days for this algorithm to become on Grandmaster expert. Actually, to pass the line of being a Grandmaster, it took it like 8 days. And then it was able to compete with the top players in StarCraft League. Okay, but how this whole reinforcement learning works, how it looks like, what makes it so special, and how actually the computer can play a game. So first of all, we have something that's called an environment. So basically, it's defined the rules of the game. Then we have an observation, so the current state of the environment. For example, it can be a print screen or a frame from the game, or just set of numbers if it is enough. Next, we have action. Simple. Go left, go right, like on this breakout game, or like in Pong or in any other game. And then the environment gives a player, called also an agent, a reward. If the action was good, usually the reward is positive, like +1, +10, something like that. If the move was not that great, the reward is negative. So we're somehow punishing the algorithm for taking a bad decision. So, for example, in that game, it would be like +1 reward for hitting a brick, +100 for clearing the entire screen, -50 by dropping the ball, and if the ball drops 3 times, just end of the game, end of episode. In more formal way, we can draw something that's called canonical agent environment loop. So we have an agent that takes an input, the current state, knows what the state of the environment currently is. It takes an action. It tells the environment what the action is. Then environment modifies itself, emits another state and reward to tell agent how bad or how good it was. So, formally, we could model at least some of the simple games like a Markov decisioning process, because we have a sequence of states, we have sequence of actions, and actually from the theoretical point of view, an action just creates a transition in states. So we move from one state to another one. And an agent is the learning and the acting part of the algorithm of the reinforcement learning problem, which tries to maximize the reward, the entire reward over time. What is environment? Environment is everything that agent is not. So the agent interacts with the environment directly or indirectly, and the environment changes as agent performs actions. Each action is considered, as I mentioned before, like a state transition. And every action yields a reward. Next, we have a state. So every scenario that agent encounters in the environment is formally called a state. So it's a state of the environment, and agent transitions between different states by performing actions. One thing to mention here, that there are states that are called the terminal states, which agent cannot transition from into another one. Like, for example, it's end of the game, or winning the game, something like that. It all depends on the game. An action is a method for the agent to modify the environment, and the agent has to decide which action to take. In some games, like Pong or Breakout, there are like only 2 actions, move left or move right, and you can think about how the agent can decide about the action. Okay, in the simplest case, we can just take a random action. Just don't care about the result, because we are going to play 100 million times the same game. And the beginning, we just have a 50-50 chance of going left and right, and then let's see how this distribution of probability should change over time, given the observed state. And the reward is just a numerical value. This is a numerical value associated with the action, and this is what the environment gives as a feedback. Okay, so at this point I would like you to appreciate how difficult the reinforcement learning problem is. Because when you're playing a game, it's not like there are only like 2 moves or 3 moves and game over, so we could simply know or easily tell which action gave us win or which action caused us to lose. We have a lot of sequences that are called trajectories of, for example, up, down, up, down, up, down. Okay, I won. Second one, down, up, down, up, oops, sorry. And each action yields a reward. We are summing the reward over time. But at the end of the day, down the road, we have no idea actually which action led us to our success. So this is not easy to say, to tell actually if it was the movement in frame 10 and then in 20th and then in 47th. No, there's no way of telling this kind of stuff. So this is something that is called a credit assignment problem. So we'll try to tackle this in a few moments, but in general, we can simply say that for simple problems, we can say that we don't care. Because even if the algorithm is, let's say, modifying its weights in a way that are not super optimal, on average, the good moves will statistically yield higher rewards than the bad ones. So let's take a one step back to the supervised learning. How many of you are familiar with what supervised learning is? Okay, some of you. So in one sentence, supervised learning is something that we have the input, we calculate what the output is according to our algorithm, our model, our policy, whatever we call it, and then we have a true label, the ground truth information about what the proper outcome should be. So in this case, for example, if we had a programmer in Pong, the programmer would say, okay, seeing this particular frame, I would go up. This is the right decision. In reinforcement learning, we have our reward, and it may be positive at that step, but there is no way of telling if maybe there was another trajectory or another step that maybe would yield higher reward in future. Maybe not in this particular step, but in the future. But we don't really care. We know the outcome at the end of the game. So we are waiting till the end of the game, to the end of the episode, to know if we won or not. And then we can emit also rewards and say that all those actions, although some were kind of good, made us lose. And this is where the statistics kicks in, and what I mentioned before, that if we are making good moves, on average, it should have more positive rewards than negative rewards. So even if we made like a mistake on the last step, the probability that we'll assign negative rewards to all those steps previously on average should not be that high. Okay, so I hope that you have at least a sense of what a reinforcement learning problem looks like. And I would like now to tell you a few things about a library developed at Google. This library actually was developed and used at Google, and then they decided to open source it, and it's called TF Agents. So a TF Agent is a robust, scalable, and easy-to-use reinforcement learning algorithm library, and this was designed to work seamlessly with TensorFlow. So actually, why use TF agents? Because I bet if you tried to do reinforcement learning, you can name at least 2 or 3 other libraries that are right on the market. So first of all, this is really great for learning, reinforcement learning, because it works seamlessly with Jupyter notebooks, with Colab, There are a lot of examples, there are tons of documentation, and they really made a great effort to make it easy to use. Second of all, it's well suited for solving complex problems because you have a lot of algorithms that are state-of-the-art for reinforcement learning already implemented for you. So you can just simply test them. It's relatively quick to develop a new algorithm, and it's pretty well tested, and it's really easy to configure. Something is called gymconfig, if you're familiar with it. If not, just Google for it. It's a way of modifying the pipe, for example, Python code using a config file. And what's more, it was designed for TensorFlow 2.0. So with TensorFlow 2.0, we have an eager mode enabled, which is pretty cool. And for those who are not ready to transition to the new version, it also works with 1.14. What's more, it was built for TF.0, so it's relatively easy to develop and debug code using the eager mode, so you can see the outcomes of your actions immediately without creating an object called session, which was a nightmare for most of the developers during the TF 1.01x era. And it also uses TF Keras to define your networks. So if you're unfamiliar, Keras is a framework that is on top of, can be on top of TensorFlow, it can be on top of many other deep learning frameworks, like, for example, PyTorch, and it's like high-level API to neural networks. So you can create your network really fast, really easy, and use it as your agent for the TF agents problem. And what's more, you can also create your computations. You can create your function that does the computation for you, annotate it simply with one line of code, thus add tf.function. And if it's not too sophisticated, if it doesn't use any like third-party library to do the calculations, it will be converted to TensorFlow graph. So it will be embedded into TensorFlow graph to speed up the computations and take full advantage of all the developments that Google made, for example, to run the code on TPUs in the cloud. Also, it's really extensible, it's easy to use and modular. So it's not something that, you know, this is like a religion for reinforcement learning, but it was designed and meant for you to develop algorithms faster. So with TF agents, we have a pretty cool landscape. So on the left-hand side, we have all the data collection, because while we are playing the games, we are going to collect the data. This is the way the algorithm learns new things. So we have the agent, we have the driver, we have our environment. So the driver drives how the game should look like. It collects all the trajectories. Then the trajectories are being sent to something that's called replay buffer. It's pretty cool piece of code because it allows us to do many fancy things. I will come to that in a moment. And on the right-hand side, we have all the things that are connected with the training pipeline. So we have all the data, like a data set or a log of the games we just played, and we are going to transfer and all this information to our model to allow it to make better decisions. So this is the time for the first example. This is one of the classic ones. This is a classical control problem where let's imagine that we have a pole in your hand, even like a mic. I will not do it with this mic. But we want to kind of fight the gravity. So we want it to stay up. We don't want it to drop. We don't want it to fall. And this is kind of a game. The environment is, as you see on this slide. And the actions that you can take is just basically move the card left or move the card right. So if you move the cart too many times to the left or too many times to the right, you are leaving the screen, so this is game over. And also, is this pole drops, because actually in the rules of the game, it says that if it's more than 15 degrees from the vertical, this is also called as a lose. But we are, let's say, getting a reward +1 each frame or each step that the pole is up, that it has not fallen. So if you were to start from the scratch, we would implement an environment. And again, nothing stops you from creating the environment yourself, developing all the code yourself. But Google provides us with pretty nice abstraction layer. So simply, you have to define only a couple of things here. One is called the observation aspect, and that defines what the observations are. So what an agent can observe from the environment. Then you have to implement an action specification. So what actions are possible, like move left, move right. Then we have to create a set method. So something that actually accepts the action and updates the state of the environment. And a reset. So simply, if the game is over, just reset the environment to the initial conditions. So we are playing from the beginning. Okay, how we could approach this using the OpenAI Gym? We simply load this experiment. We simply load this environment. It's everything that everything has been already prepared for us. So we have the observation, we have the action, we can load it, we can inspect it, and we have all the things ready for us to start playing, to start developing the algorithm, how to make this pole stay straight. You don't have to take care of all the cumbersome and tiring part of coding. It's just for the developer, actually for the researchers to test their ideas of the algorithm. So we are trying to balance the pole. And in the first line, we just simply load the cart pole. Then we define the policy. So in the simplest case, there could be a purely random policy. So we randomize if we should move left or right. And then we just play the game. While it's not the last move, just randomize a step according to the policy, given the current situation, then do the step. So environment has to update itself, and then we just collect new reward. Please don't be scared about the math, because it's not the core part of the presentation, but this is something to make it more solid, maybe, or look fancier. Because the nice things are starting when we are going to put a neural network or any other more fancier algorithm inside our reinforcement learning algorithm. So the neural network takes in the observations or an image. Actually, in the case of the cart pole, it's just a vector of numbers. For other games, it can be just simply a screenshot, a frame from that game rendered. And it's about to emit probabilities of actions to be taken. And how to do it in the best, maybe not best, but in an advanced way. There's a strategy that is called policy gradients. And we are going to emit the probability of taking a left or probability of taking a right. And this is parameterized by all the weights that are in the network. And ultimately, the goal of the algorithm is to be modifying those weights of neural network over time to maximize the expected return. And as you can calculate, you can just calculate this analytically if it's possible, but it sometimes may be hard, or maybe it's not, from computational point of view, is maybe not the fastest way. So we are just going to play 100,000 times the same game. We are going to collect all the trajectories, and actually we're going to use a Monte Carlo estimation of the return. So with TF agents, we are just loading the environment, again from the OpenAI Gym. We are converting it or wrapping it with something that's called TF by environment, and this is all what we need, because we have all the specifications of the observation and possible actions, and in the middle of the screen you see that I simply created a network. So a couple lines of code, and the only thing I had to give to this piece of code is the information about what the input is, what the output is, and that we have a neural network inside that has 2 dense layers with 32 and 64 neurons. And that's all. Then we're just playing the game. This is another time when the replay buffers kicks in, because there's the way of how we can store the trajectories, and it also provides a number of utilities for us to use to collect the data and to play the game using things that's called drivers. And because it's going to iterate through the collection of the data and actually boost the training time of our algorithm. And the second example for today is the game breakout. Again, we have our environment, we move left and move right, but this time, if you inspect the code for the specifications of the environment and actions, this time we are not getting a simple vector of like an angle of the pole, but we get like a print screen. So it is a frame from the game. So it would be like 84 by 84 by 1 pixels. And this is the input to our neural network. And in this case, we are also going to emit the observations. Should we move left or should we move right? But if I play the breakout for a while, I think I would be able, after some time, to tell if moving left would be better or moving right. I mean in a long term. So it would be really, really cool if we could predict the future outcome, the future reward of our algorithm given the previous steps. So should I go left or should I go right? So if only I knew what is going to happen, it would be relatively easy. But somehow I can approach it a little bit differently, because I can try to estimate or try to predict the future outcome. So instead of that, we are going to estimate if we should move left or if we should move right. And if I move left and it worked pretty well, okay, then I should increase my expectation of winning. And if I moved left and it was not a good idea, maybe I should decrease my expectation of winning the game. So we can formulate it again using a couple of fancy equations. So basically, we are taking an expansion over the sum of the rewards from the future, and we are going to discount it by the coefficient called gamma to bring it to the current time. So this is going basically to tell us, given some state and the possible actions, which action should be better. So this is kind of an action critic, if you want to call it that way, because I'm saying that I want to take some action, and there comes another guy and says, I think that if you did something differently, your outcome will be higher. So if we only knew those Q functions, it would be cool, but we don't know. So we are going, to estimate them, and we are going to actually calculate them somehow simply by playing. And we are going to compare over the time the expected returns that we calculated over the game with the actual ones, which we know after we play the game to the end. So we know if we made a good prediction or bad one. So this is conceptually, it is pretty similar to what we have seen before. So we are going to have another neural net, and in this case, it will output not the probabilities, but those Q values that are the future expectations of the returns. But in general, the idea is the same. And this is another few lines of code. Again, as you can see, this is relatively simple. We are just building a Q network. We are building deep Q network agent. We are going to train it with just a bunch of lines of code. It's not cumbersome. You can have it in like just copy paste it, and you can use the same algorithm for another problem, only by creating a different specification of input and output. That's all you have to do. And playing breakout can be faster in Tensorflow, because imagine that you have to play 100 million of times, and if you have 64 cores, you can play 64 games at a time. And again, if you were to create the library for reinforcement learning yourselves, you would have to implement it yourselves, and in this case, it's already here waiting for you. And the last but not least, because I think my time is coming to an end, the famous replay buffers that I mentioned a couple of times during this presentation. This is a pretty cool thing, because it is a way that we are storing the trajectories. So this is the way we are storing all the progress during the game. So all the actions that we made and all the states that were emitted by the environment. And imagine a situation that you played really, really well, but let's say the last move was the best bet one. So if you were to randomly create the same state, I mean, it would take you quite a long time to actually repeat the exact same sequence, differing only by the last one. But with replay buffers, you don't really have to do it, because what replay buffers allows you to do, they allow you to sample some parts of those sequences, some parts of the trajectories, and then simply replay it to that certain point and then take a different action. So it really speeds up all the computations. And also, from the purely computational point of view, it uses a structure that is called TF dataset. And this dataset is the optimal way. There is no better way to feed the data to TensorFlow, especially if you are using a GPU or TPU environment, because then it minimizes the time that the GPU has to wait for another batch of the data. And the last slide with a couple of links for you. So the first one are the links to Colab. It's a Google Cloud environment for playing with Python and with TensorFlow. And you have the full tutorial of TF agents explaining everything that you need to know and you want to know. Then you have a couple of resources about books about reinforcement learning. Actually, one by Sutton is like, I think if you ever wanted to start your journey seriously with reinforcement learning, you sooner or later you would come across this book. And it's available as a PDF file, and it's free of charge. You can simply download it and print it or read it or whatever. Also some slides, some lectures online, and some lectures as HTML files on the internet. Okay, thank you.